Thanks for joining with me today. We're going to go through the Astronomer of the Week for this week. It's the woman who measured the universe, Henrietta Swan Leavitt, and the cosmic yardstick. Here you can see Henrietta Swan Leavitt at the age of about 30 years old. And in the vast summit reaches of the cosmos, there are a few names that should hold as much weight for the backyard observer or the astronomer as Henrietta Swan Leavitt. While we often think of astronomy as a pursuit of great telescopes and high-altitude domes, Leavitt's revolution happened on glass. Thousands of photographic plates that shattered the bowl of the sky and turned a flat firmament into a three-dimensional universe. Let's learn a little bit about her. Here's her story of the woman who gave us the yardstick to the stars. Born in 1868 in Lancaster, Massachusetts, Henrietta was the daughter of a Congregationalist minister. Her path wasn't always aimed at the stars. She studied a broad curriculum at Oberlin and then the Society for the Collegiate Instruction of Women, which we now know as Radcliffe. It wasn't until her senior year that she took an astronomy course and caught the bug, which many of us have. After graduation, she headed to Harvard's College Observatory. In those days, the director, somebody you may have heard about, Edward Pickering, was busy digitalizing the sky via the new technology of dry plate photography. He needed computers, not the silicon kind we use to process our CCD images or what I'm recording on today, but human ones to analyze thousands of glass plates coming in from Harvard's Southern Station in Peru. And here you can see her actually analyzing a plate. Leavitt started as a volunteer, but her talent was undeniable. Even as a progressive illness led to her becoming almost completely deaf, her focus only sharpened. She wasn't looking through a telescope. She was hunched over a light table using a magnifying loupe to compare positive and negative plates of the small and large Magellan clouds. While cataloging over 2,400 variable stars, half of all the known variables at the time, Henrietta noticed something extraordinary. In the small Magellan cloud, she tracked a specific type of pulsating star called a Cepheid variable. So you can think of a Cepheid variable as the heartbeat of a distant galaxy. While most stars like our sun maintain a pretty steady light output, a Cepheid is a star that physically grows and shrinks in size, causing its brightness to pulse with incredible regularity. Because these pulses are so predictable, they are the most important standard candles in astronomy, tools we use to measure the vast distances in the universe. She realized because these stars were all part of the same cloud, they were all roughly the same distance from Earth. This meant that their apparent brightness on the glass plates was a direct reflection of their intrinsic luminosity. In 1912, she published the period luminosity relationship, now known as Leavitt's law. She found that the brighter the star was, the slower it pulsated. If you knew how long it took to go from dim to bright, you knew how much light it was actually pumping out. By comparing that to how faint it looked at another observation, you could calculate exactly how far away it was. It's hard to overstate how much this really changed things. Before Henrietta, we were mostly limited to stellar parallax. And I have a definition of stellar parallax below. We'll go through it in a minute. It's a method that only works for stars right in our backyard. Leavitt's law became the standard candle. A decade later, Edwin Hubble used her discovery to find Cepheids in the Andromeda Nebula. He used her yardstick to prove that Andromeda wasn't just a gas cloud in our galaxy, but a city of stars millions of light years away, another galaxy. Our universe suddenly grew from one galaxy to billions. Final reflections on her: Henrietta passed away from stomach cancer in 1921 at the young age of 53. She died before she could see the full magnitude of how her work reshaped the cosmos. In fact, a Swedish mathematician once tried to nominate her for a Nobel Peace Prize in 1925, not realizing she'd already been gone for 4 years at that time. Next time you're out with your telescope scanning the southern horizon for the Magellan Clouds if you're in the southern hemisphere, or hunting for Delta Cephei, the prototype of her variables, or in the summer at one of the best Cephei's, Eta Aquila, take a moment to think of Henrietta. She never had a PhD, and she really rarely got to spend her nights at the telescope, but she's the reason we can look at a faint smudge of light and know exactly how far we're looking into the deep. Clear skies, keep looking up, and this is just stellar parallax. If you're unfamiliar with it, here's just a simple thing on it. In the simplest terms, stellar parallax is the apparent shift of a nearby star against the background of a much more distant fixed stars, caused by Earth's motion around the Sun. It was the first successful way we ever measured the distance to another star. It's kind of like the finger test analogy. You've probably done this. You can hold your finger out at arm's length and then close your left eye and then swap it with your right eye, and you'll see your finger will jump back and forth against the wall, or in this case the camera in front of me. Now move your finger closer to your face and try it again. Okay, the jump is much larger. That's the core principle. The closer the object, the larger the parallax shift. In astronomy, our eyes are the Earth at two different points in its orbit. Observation 1, we take a picture of a star and say January. Observation 2, we wait 6 months until July when the Earth is on the exact opposite side of the Sun, about 186 million miles away from where it was in January. The result, the nearby star will have shifted slightly compared to the incredible distant galaxies or stars in the background. The problem with parallax is that the shift is tiny. Even the closest star to us, Proxima Centauri, has a parallax of only 0.77 arc seconds. Ground-based limits from Earth atmospheric turbulence seeing usually spear stars to about 1 arc second. This makes measuring tiny parallax shifts very difficult. The wall before space telescopes like Gaia, we can only use parallax for stars within a few hundred light years. That's exactly why Henrietta Leavitt's work was so explosive. Parallax only worked for our immediate neighbors. Her Cepheid variables allowed us to leapfrog past the limits of trigonometry and measure things millions of light years away. She truly was an amazing woman, an amazing human. Just her work really transformed and laid the groundwork for Hubble and for modern astronomy and our study of it today. Hope you found her interesting. Hope you take some time to look at some other sites about her. Well worth your time to learn about her. Thanks for joining me. We'll catch you next time.